Right, so in this video, we're quickly going to be looking at histograms and box plots, and which are used for checking numerical distributions. Previously, we've seen pie charts, bar charts, and different ways we can plot in our bar charts and pie charts. We've also seen the line charts, like using all of the three visualization libraries. So we're also going to do the same for histograms and box plots. Now, histograms, like we've rightly established, are used for, of course, visualizing the distribution of any numerical variable. And you can go back to the first tutorial where we discussed about all of these visuals and learn more, of course. So we are going to do this, and of course, we're going to see things like the bin size, which I think I made mention of that. It's just basically the size of each class. I mean, what a histogram does is that it takes a data set, then it breaks it into several intervals. For example, if we have an age, and break the age column into, if we have an age ranging from 19 to 55, breaks that age into smaller classes like 19 to 24, 24 to 29, things like that. So that's what we're going to see now. And of course, let's start with the matplotlib already. We have that imported as PLT. Go to just use PLT, but histo think hist think hist does it. So plt.hist, of course, you can see this guy is already giving us a hint. So we pass in the column that we're going to use, df dot, oops, yeah, of course, I'm going to pass in the each column. Let's see what this looks like. Of course, now you can see what we have here, right? Let's add the plt.show so that we don't have those noise. And now we have, so automatically what the histogram, what this guy does is that it divides whatever data you have into 10 different bins. And bins is like the size of the class, like the number of intervals. So here we have one, you have two, you have three, you have four, you have five, and that one here six, seven, eight, nine, then you have 10. That is the last bin. So bin is the number of classes. Now this number of classes are not computed carelessly. Of course, I like Plotly because it automatically computes that for you. But if they are not computed carelessly, we choose the number of bins carefully. And of course, you can feel free to pass in other things like your PLT dot, of course, these guys will do. So the number of bins now, let's just quickly look at some things to consider about the number of bins. Just do this quick search so that you keep it in mind. I'll just show you two ways and you can go and find the other ways for yourself. So the best way out of the box is to use the square root of the number of samples you have. That is the number of entries you do have. So of course, when you use the len function over the data set, it's going to return the number of rows you have. So just take the square root, and then that gives you the number of the number of what do you call it now? The number of bins to use. So let's go back to our page. Let's do this somewhere here. Let's do len of df like this. And let's compute the square root. It's just power 0.5. If you've not forgotten this trick, one way to compute your square root is just to use 1 over the number, right? And you do this, then you have that. Now you can see it's 8, right? So I can just pick up the 8 and bring it here, or I can dynamically just compute it. So I can come here and add something like bin size is equal, oh, let me see, bins, let me pass it this, is equal to, let me compute this guy, let me copy this guy and bring it here. But I think we will have issue with this because it expects a whole number to be passed. So we're going to convert this guy to an integer. We're just going to round, use the round function to just round it up, right? Or up or down as the case may be. Because this will round it up to the nearest integer. Let's do that. Let's just copy this. Oh, all right, 8. Right, so we're just going to do this to 8, and I'm just going to pass it bins here as equal to bins. Yeah, so run this. you see that it will change. Now you can see right, it has changed. Now this has broken it down into 8 bins, right? And you can see something. I'm going to mention something about skewness. As you can see now, the data is more concentrated towards the left and towards the right, right? So there's what we call a normal distribution, and I spoke about it in the previous class, right? I spoke about skewness, right? So you can see here, these are the tails of the graph, right? These are the tails. So the longer the tail, where we have the longer tail is where the distribution is skewed to. And you can see that we have a longer tail towards the right. Right? So if you don't understand these things, just go back to the first video in this series where we spoke about um, these distributions, right? So this tail is longer. Of course, we're going to see this when we go to Seaborn plots. So I'm going to plot now. The age distribution shows us you can quickly see that from this distribution that this 60 is likely this age that is here is likely an outlier. Right? It's likely an outlier. And of course, you can use the iterative method to add the labels to your chart. But from this here, we can see that this value is like it's an outlier. It doesn't belong here. Right? Well, it actually exists because someone who is 60 years old can actually apply for the class. Right? So these are what we call false outliers. They actually are values that, even though from our analysis, they are categorized as outliers, but they really exist and they are not erroneous entries. So we can still call them, we can still allow them in. We don't just filter outliers until we are sure that these ones are actually true outliers, right? So now the box plot also shows us outliers, right? We're going to see what the box plot does in a minute. So I'm also going to be doing plt dot box, same thing, just going to be passing the each column as what I want. I want to do them together because together they are used for okay. Let me see. I'm the one that is mixing it up. Plt dot, please let me see suggestions. Box. Let me see. Okay. Plt dot box on. Yes. Okay. I was actually expecting. Yeah. Let's see. The page. Okay. Let's put dot all and see. All. Okay. I don't know why we are having this, but I'll just go ahead and use the C1. Of course, we're going to look at why we're having this error. Okay, let's just look at it up with AI. I really don't use this one for, I don't use this guy here. So let's just copy this and ask why we're having that error. Explain error. Yeah, let's try to see why we're having that error. So I'm trying to make some explanations here because once I leave, yeah, I'm just going to show you how to implement this with the other libraries so that this video won't be too long. Of course, instead of PLT, okay, box plots. Oh, okay, right, I get. So it's supposed to be box plots, not box. So accept our one. Thank you, AI. So you can see that here, right? So now you can see that it is trying to show you the age distribution. This is only one box plot, right? Now you can see how we have some values here that are described as outliers according to this. So these are the whiskers, which are the lower threshold and the upper threshold, and you know what they are, of course. They are the I think the IQR, right? Minus am I sure? Yeah, the lower threshold is the 25th percentile, like minus the minus 1.5 times the IQ. think. Yeah, that's that. And same with the upper threshold, which is um 1.5 times the IQR plus the 75th percentile. So these are the whiskers, right? And this here is the 25th percentile or lower quartile. This is the upper quartile. This is the lower threshold. This is the upper threshold. You can see any value that is above here is described as an outlier. This is our age 60 something for that other person here. So you can see it's not just that age that is seen as an outlier. Like even some uh, three edges here, three other edges here are seen as outliers. So we have in total four outliers. Right. And you can also color this. I'm not sure if this will work here, but let's try. I'm not sure if box plot to color it. So let's see by, let's see DF. And if it doesn't work, fine. All right. So it doesn't support that. So let's see the same. It's so of course I've explained box plus number of times, like a couple of times, and how it shows us some very, very important information. So you can see that even though histograms are great for visualizing our distribution, to see the kind of distribution our data follows, you can quickly be able to use box plus to be able to spot outliers right quickly. And let's do the same with Seaborn, SNS for box plot as well. Then when you do this, you're going to have data is equal to df, x is equal to age. I just collected this, just passing x equal to this. If you want to have a, you can see here, right? So if you pass in x as the age, now you're going to have a uh, you're going to have a horizontal, what do you call it now, box plot. And just for legibility's sake, let's use our plt.figure. Since this guy is not always dynamic. Size is not always dynamic. So let's do this. Now you can see here what I have. So this is pretty much a bit dynamic, right? You can see the box plots and you can quickly spot the outliers that are here. So this is just using SNS, right? And of course, you can add the dot title, y label, and of course the dot show. Of course. So I'm going to now show you how to do the, of course, histogram with SNS. So it's just hist plots as well. Because let's use the average score this time around. Data is equal to df. Let's use x is equal to average score. Average SNS doesn't have hist plots. Okay, hist plots. Correct. Now you can see, right? So of course we can dynamically compute the bin size. Of course, we're still passing the bin. Don't know. Bins, yeah. Bins is equal to and dynamically pass the bin size we did earlier on as bins, right? Then we run this guy. Now, here is what interests me the more. This is for average score, right? You can do, let's stick with the gender so that we see, let's sorry, age rather, so that we see that what we are doing is actually consistent all throughout. Now you can see this looks similar to what we had here, right? Gives you this hist plot. And of course, like we rightly established, you can turn off this grid, right? By plt dot grid, if I'm not mistaken. Visibility equal to false. Do this, you have this. You do not want the grid lines. Now you can also use plt dot figure to expand this. Let's do that. Figure, right? Fig size, because let's do this. All right. Yeah, so we have this. This is at least more legible than what we had earlier. So the thing is that there is no clear-cut way to know which place you're stopping here, right? These guys are stopping, but I'll show you a way which will show us that. Now, that leads us now to plot the visual, right? Now you can still see our 60 somewhere around here. And let's see how to do this quickly with Plotly. So of course, it's PX, and you just bring it as histogram. Then of course, I'll just the data frame is equal to df, and of course our x is equal to age, right? Then bins is n bins. Here in Plotly we pass in n bins, not bins, right? N bins, that's just the difference. And then you do this. You can see it's almost the same distribution as you do have, except that this time around, of course, I can go ahead. So let me take out these n bins. Automatically, Plotly calculates uses the best method possible. Remember the previous methods I told you is this guy. This is the quick method, not really the most robust. You have the Sturgis rule, which is 1 plus 2 times log to base 2 of n. Log to base 2 is not difficult to compute. You can use the math dot log function, dot log 2 function to calculate that. Then you add 1 to whatever it is that you get. You can also use the IQR technique, that is Friedman Diaconis rule. You can use that to compute. You can use the Scott's normal reference, right? But for each case, read under. Right? That's what makes you a better data professional. That you understand the best uh, value to use or the best approach for every data. This one assumes that the data is normally distributed. If the data is not normally distributed, um, of course, I know most numerical distributions might be normally distributed, might follow normal distribution. So if it doesn't, you can now come back here, right? He said best for data sets with outliers, right? If you have data sets with outliers, this is the most robust way to compute, right? But guess what? Me, you do not have time to do this. So try out this and let me see what you have. So now, why I like the plotly visual is that it automatically computes this. And once you hover here, you can see the age. It's giving you the age. This is 15 to 19. This is 20 to 24. This is 25 to 20, right? So we have 1, 2, 3, 4, 5, 6, or 7, 8, 9, maybe 10 or 11. I'm not sure. So this shows you that, and you can even if you want to see the count easily with Plotly, you can just pass in your text auto equals to yes, sorry, true. So there was something I was going to show you about this guy. If you want to get the something like the normal distribution curve, that is what we call kernel density estimation, KDE, kernel density estimation plot. You can just pass in KDE here. It's equal to true. Pass it in. Now you're going to see it is going to overlap this guy. Now you can see. So now you can see where the tail is. This is the normal distribution, and this is about the median value. Now the median value should be located around here, right? Now this is the left tail, this is the right tail. Now because the right tail is the longest of all the tails, we call this a what? A right skewed distribution. This is a normal distribution, but this is a right skewed normal distribution, right? So that's what I wanted to show you. So that's one advantage of using the CBOM. It allows you to easily just get the KD out. You can get the same with this, but you have to do some kind of manipulations to get that, right? All right. So that's that. And of course, for here, you can also quickly pass in this guy. You can also easily pass in this guy here. Title, of course, our title will get, that's not what I wanted to pass in. Another optional argument you can choose to pass in is if you need to pass in your end means you can do that. But we can also pass in the color, right? We can also pass in color. Color is equal to let's say gender. So let's color it by gender. Let's see the distribution of age by gender. Now you can see, right? So we have 5 females that are between 15 to 19. Now we are adding more explanation. Instead of just seeing 7 in total, we are now seeing that out of these 7, 5 are females and 2 are males. And of course, we're also seeing here that we have 14 males that are between 20 to 24, we have 19 that are between 25 to 29. So you can see all of that. And you can see that the oldest people in the house are the males, right? The oldest of females are between 30 to 34. So that's data analysis, bringing out insights. You're not telling people, okay, so look, who the people that we have that are elderly are actually males, right? And you get to understand, okay, because of course, teaching elderly men and teaching also elderly females is a different use case entirely, right? It's a different use case, especially women that are between this age now to this age. You expect that they already are having children responsibility. And of course, you have to be flexible with your timing, your decision making, and everything. Right. So I just so kind of love data because you are not just making assumptions, you're making decisions based on facts that you already have. Right. So that's another thing that I like about this. And of course, this is not just the only thing I like about this. Let me just copy this so that we're not doing too much on one plot. Last thing to say is that if you need a box plot, you can just pass in this guy here. You can just pass in what we call marginal, pass in a box here. Marginal equals to box. You have a box plot inside of a hist plot. Now you can see how this thing is very, very easy, right? You can be able to spot, now you can see the outliers. You can see them there. You can even see the ages that are the outliers. You can see it's 35, it's 36, 39, and 63. Those are the outliers. And now you can easily see when you hover here, you can see the minimum is 16, the lower firms, that is the lower threshold is 16 as well. Here the maximum, this is the maximum, right? This is the maximum. It's not the same thing as the upper threshold. Here the lower threshold and the upper threshold are the same, right? So this is Q3, this is Q1, just visually easy, right? You don't have to even cram the positions. You already are seeing what this guy is showing you, and this is showing now that the median is what, about 25, right? So that's very, very cool and easy. And if you decide to pass in the color, as AI is suggesting we do, you'll now be able to see the different plots. You can see it has um, the age distribution for males and it has also the age distribution for females. I mean, in terms of the box plots. Now you can now see that for females, we do not even have outliers for females. When you're considering only the female gender, we do not even have outliers. But when you're considering the male gender, you can see that we have outliers both to the left and to the right. Right? So this is a deeper data analysis. The deeper you go at interrogating your data, the more insights you get from the data. Right? So see you in the next tutorial where we discuss, I think, scatter plots. I'll see you there.